Good morning, good afternoon, good evening, wherever you might be, and welcome to a talk that I gave back in March of this year at a company named Ida Labs in Berlin. And I will attempt to recreate what I said there. I believe I started off by introducing myself and explaining that I grew up around the buckle of the Bible Belt in a city known to marketing companies as the taste buds of America. And then I moved to Germany, where I got my PhD in physics. And since then, I did a postdoc and I quit to take better care of my kids and write books and sometimes give talks about black holes. Something I did not study as part of my PhD work. But what inspired this? Let's see. Around the time when I was going to give this talk, I had been at a party with some neighbors, and we were discussing a few things. We talked about outsourcing component manufacture. We talked about moving to an island to avoid a collapse of civilization. We were at that time consoling our children over burnt koalas because that was when all of the fires in Australia were raging. We talked about eating probiotics to avoid brewing alcohol in our guts, about avoiding cosmetics that make us stupid. And we talked a little bit, I think this was before the coronavirus got started. So that had not yet become a theme. But even before the coronavirus was with us, we had this sense that a darkness had fallen over the land, at least from the perspective of my neighborhood. But I was trained to be a scientist, so I have been indoctrinated with the belief that scientists will save the day. At least this is what happens in Hollywood movies. We know, real scientists know, of course, that we try to rigorously characterize the problem and propose some solutions with appropriately defined error bars, which will be misinterpreted by the media and by the politicians making the decisions. Rather, we know that scientists will diagnose the problem. And this gets complicated by the fact that in recent decades, the concept of the scientific method seems to have changed within many circles. So within the old scientific method, you would gather data, you would plot your data and interpret your data. You would use frequentist statistical methods. Your hypotheses would be falsifiable. They would be directly observable, and you would have a control variable. But in the new scientific method, you might start by filtering out some puzzle pieces and putting a puzzle together and interpreting that puzzle. You would use Bayesian statistical methods. You would talk about paradigm shifts. You'd use inferred observations, and you would not have a control variable. The problem with this new scientific method is that not all puzzle pieces are equally good. When two overlapping puzzle pieces agree, you may decide to keep them. And when a puzzle piece disagrees with other pieces, you may decide to throw it away. This can work, but you do run into problems if you zoom in too much. You don't want to accidentally measure the measurement tool or the noise rather than the specimen. When you use a feedback loop to converge on a set point, the effect of the feedback loop might be hidden from the error analysis. For example, if the light in the microscope produces and samples the same effect, you can't tell if the effect would have occurred under different conditions. One must be especially careful when using newer methods. For example, Bayesian analysis of networks has become very popular in recent years, and it frequently obscures and underestimates the impact of assumptions, or otherwise known as priors. In short, a modern researcher must be very careful not to pick and choose data, overfocus, hide errors with hidden feedback loops, relying on unverified assumptions. Whenever these things are done, the scientific method is not being rigorously followed, and you might accidentally trick yourself into believing in a result that is not true. Whenever there are common mode sources of noise or systematic errors, you might accidentally filter out a picture of something that you didn't intend. For example, a person who reads another group's research must be aware of all of these issues and be on the lookout for sloppy or fraudulent activity, because, as we've seen even in the top journals, some researchers are lazy enough to take a single bit of data and slice and dice it so that it looks like it was data from multiple distinct samples. This was something that happened in a coronavirus article in the journal Nature. These issues might seem like they should only concern scientists, but because our academic institutions train far more scientists than they can employ, all of these scientists go out into the broader community and sell their work to companies as data science. In my city, an ex-academic can take a crash course and rebrand himself as a data scientist within 2 weeks. But what sort of training have these people gotten? Is the academic system adding a lot of value to them, or is it making them worse by teaching them to delude themselves and cheat? So this sketch right here, it's not completely mean-spirited. It is a sketch from a satirical novel called Gargantua and Pantagruel that was supposedly written by a man named Rabelais in the 1500s. It was the story of a giant baby that a town fed and pampered in the hope that he would grow up and protect them. The end result was rather scatological. If a group managed to Well, I first saw this image in the form of an inside academic joke about big science institutions or large government-funded projects that train people like data scientists. So the government subsidizes the production of data scientists through their facilities, at which young men and women learn how to make images of atoms, images of proteins. They do CERN particle identification. They might measure gravitational waves or take images of black holes. And each of these measurements requires a student to reconstruct an image or signal based on fragments buried in noise, and they are often constructed in ways that are difficult to reproduce. For example, an image of an atom was constructed in 2013 by using a laser to eject individual electrons from a beam of hydrogen atoms. A toroid was used to amplify the angle of ejection so that the image would be large enough to see, but only some of the atoms had the right excitation and orientation. How did they choose which atoms to use in the image construction? How did they eliminate common mode errors from the toroid? What was their control variable? None of these questions are answered in the scientific publication. Yet, this image of an atom is the first thing you will see in a Google search, and it doesn't appear that any other research groups made a similar attempt, since the image only ever appears in a single color scheme. This is not the scientific method that I learned. I thought people were supposed to do experiments in many different ways before you believed them and made them the top search result for image of an atom. I find it strange that this image was taken by a small research group in the Netherlands in 2013. And today it is the only picture of an atom that can be found through Google. I was taught that the scientific method requires that multiple experiments should be done by different groups and with different methods before one should believe a result. But this does not appear to be the case with this image of an atom. Yet teachers everywhere will find it via Google and show it to their students. I always believe the data, but I don't always believe in the interpretations or the conclusions. And this is one of those cases. I just don't see how they distinguished the effect of the toroid from the effect of the hydrogen atoms. When the hydrogen beam is off, they have a sort of control variable, but it isn't really a very good control variable. It would have been better if they'd had a different sort of particle that is similar to hydrogen. In that way, they could distinguish the scattering effects from different sorts of atoms. Otherwise, they are just comparing a scattered beam to a non-scattered beam, and it is entirely possible that all of the modes they measured had nothing to do with hydrogen, and they depended entirely on the measurement device itself, the toroid. Their cross-sections have the same shape after all, as far as we know. Even if they were really measuring modes of hydrogen and not of the toroid, the hydrogen atoms would have had all sorts of orientations, and I wonder how they would select which data points to keep and which to throw away. Questions of this sort also arise when X-ray crystallographers take images of proteins. Since 2015, there has been a holography method to cross-check crystallography images, but it has only been applied to 3 proteins as far as I know. I wonder if there is a house of cards of crystallographic data waiting to fall. Synchrotron light, the reason I believe this is that synchrotron light may hit a crystallized protein many times from many different directions. One is left with a large data set of images that must be put together like a giant puzzle. But how much do our expectations of how the puzzle should look influence the algorithm determining its construction? If fast processing of the data is used to tune the machine that they use to complete the image, has the scientific method been compromised? This question is surprisingly relevant for interpretations of LHC data used to measure the famed Higgs particle. I had the misfortune to listen to a talk by a young man who had done his PhD work on designing a Bayesian neural net machine learning algorithm to improve the number of Higgs particles detected. He was boosting and attenuating the tens of thousands of signals in the detector to teach it to measure what the users wanted, and he showed no awareness of how what he was doing might affect the error bars of the measurement or of the integrity of the scientific method. His concern was about how the turnover within the thousands of young people employed in the LHC detector community was so high that making sure that knowledge was passed on required highly modular programming approaches. The system had evolved such that the knowledge of how the detector worked was contained within the system itself, rather than within the people. Something similar appears to have happened within the black hole measurement community called EHT, the Event Horizon Telescope. Since a black hole is the largest type of particle we have thought up, I'll include it in this selection of skepticism about pictures of particles and proteins. So in April of last year, so that would be 2019, the Event Horizon Telescope took this picture of a black hole, and it landed on the cover of newspapers and news magazines across the world. The Event Horizon Telescope community claimed to have taken this picture of a black hole by combining data from many different telescopes around the world. This is surprisingly similar to what X-ray crystallographers do when they construct an image of a protein by using a collection of images that all capture different aspects of the object under study. But what was interesting about this measurement was how, unlike images of proteins, it ended up on the front pages of newspapers and news magazines, together with the face of the young project leader, who was just a PhD student while the data was being collected. When I was in school, I never thought I would see a picture of a black hole because I was taught that the concept was an extrapolation from predictions of general relativity, a theory that fails to predict the shape of galaxies that are supposedly constructed around black holes. If the theory fails, it must be an approximation, and extrapolations from approximations are stupid. If we look at this in the context of history, we see that black holes were popularized by Oppenheimer around the same time that the nuclear bomb was invented, and the concept of a hole from which even light could not escape struck a giant resonance with the hopelessness and horror of the zeitgeist. But it seems to me that whenever physics waxes poetic, it loses its connection to reality and confuses figurative and literal concepts. Mathematics is always an approximation when the map is not the territory. Despite my reservations, I am always eager to analyze an experimental design, especially if it aims to measure something previously thought to be unmeasurable. If 1.3 millimeter light is filtered out, simulations using general relativity say that there should be a hole in the middle of this galaxy. The simulations of what they thought they would be able to see didn't match exactly what they did see, but we all make mistakes. However, this is one of the things that the scientific method is supposed to teach you, that it's about making a prediction and then seeing if that prediction comes true. And if your simulation doesn't match what you actually see, that means that there's something wrong with your theory. Yet this was not emphasized at all when images of the first ever black hole were put on the front pages of newspapers. So you probably want to know more about how they took this measurement. Individual radio telescopes can't resolve this hole, but if all of the measurements of all radio telescopes are combined, this new sort of measurement might see something interesting. So, many measurements of starlight's timing and intensity must be combined in one image, even though individual measurements are a noisy blur. The gaps between measurement locations lower the fidelity of the image, and without the timing information of when the light arrived, the intensity information is meaningless. That would mean that even if you have lots of intensity data from all of these facilities, if you don't have very accurate timing data, the combined image is not usable. If you're curious, this is a rather expensive array of telescopes. They're installing a new one in Australia, and I looked up the price. The data center alone cost $80 million, and the work for installing the telescope itself was something like 6,000 man-hours. So it was pretty pricey, this experiment, to maintain this infrastructure and build it. But to get money, you have to sell your project to the public, and the way that is done today is to go on TV, go on a TED Talk. This has become part of the modern scientific method to secure the public's approval in order to justify your government funding. This was, of course, never part of the original scientific method, but it plays a very important role today. A good way to get the public's approval is to have a young member of your collaboration give a TED Talk. And if you can use a popular movie image to promote your project, so much the better. That's what this image behind her is. It's from a movie called Interstellar, where a black hole plays a central role. And what's funny about this is that if your young project leader says some things that are absolutely absurd, you really don't have to worry that much because the public isn't that clever and they aren't listening very closely. In any case, it isn't really the young person's fault. It just means that she had terrible teachers and a terrible advisor. If they would let her go up on a stage and say those things, I mean, shame on them. She said things like, I'm paraphrasing, but I can take random image fragments and assemble them like a puzzle to construct an image of a black hole. That tells, I mean, if she understood what she was saying, she would know that this is saying right from the get-go that the method you're using is invalid. If you can do that, you can't use that method. And this was sort of her sales pitch of explaining what she saw her task as, what her bosses told her she had to do. They told her that some images are less likely than others, and it is my job to design an algorithm that gives more weight to the images that are more likely. That's not how people do science, if they're instructed properly. But let's not worry about this too much. Once the young researcher has published their data and made a press release that gets those results onto the front pages of various magazines, they can now be sent off by their supervisor to defend their result in front of an audience of peers. And that was done at Caltech, and I paid very close attention to this talk and took some notes on things that were said, and a lot of very astounding things were said. That the experiment is equivalent to taking a picture of an orange on the moon. Now, if that is the case, ordinarily that would tell you that the experiment is not possible because you can't do that. There are things called, resolution limits. The detector is moving. The measurement device is moving. It limits what you can do. She talked about the challenge of dealing with data that had 100% uncertainty. Now, ordinarily, a scientist would see 100% uncertainty and say, I can't use that data, but this research group decided to use that data. She talked about using an algorithm that was guided by the user, as in the user selected regions of interest that they wanted to see more light in. They've caused the algorithm to converge on a particular image that they wanted to see. That is also not scientific. She said, most people use this method to do calibration before imaging, but we set it up to do calibration during imaging by multiplying the amplitudes and adding the phases to cancel out uncorrelated noise. Now that's wrong in 3 different ways. So I could go through all of these, but I don't want to bore you. My point is that any one of those things would invalidate the experiment. Yet this collaboration did all of those things. It's not just one error, it is an error at every single layer of the collaboration. So all of the people are making big mistakes, not just one person. So just to talk a little bit, let's see. I can say a little bit more about what it would take to get an image of an orange on the moon. So since Hubble is our best telescope and it is not affected by the Earth's atmosphere, but it still cannot take a picture of an orange on the moon because the moon moves across the sky faster than Hubble can track it. And when you combine rotational and translational motion of a detector, that limits what it can measure. It is a sort of intrinsic uncertainty that the Event Horizon Telescope people decided would not be a problem for them, even though they were trying to measure something that is light years away. Now, the next strange thing about the Event Horizon Telescope collaboration was how they characterized their measurements with a quantity called uncertainty. If I look up the meaning of uncertainty, I see it as, according to this formula. Then I think about a simple example. How tall is a person in this group? Maybe 75 centimeters, but the standard deviation is about 50 centimeters. So I am 20% uncertain. But if I measure the group 10 more times, I'll only be 6% uncertain. This is absurd, of course. Has the collaboration confused themselves with this concept? What scares me is that I've seen this approach to experiments in several physics experiments. It's very worrying. Then there's the issue of independent cross-checks. So they convinced themselves that they could still do this measurement because they were checking it in 2 different ways. But I think that just meant that they were deluding themselves in 2 different ways. In one method, they deluded themselves by hand-tuning their data with a clean algorithm that was biased by the user. And in the other form of delusion, they automated it by using Bayesian neural net machine learning algorithm that biased the priors or assumptions. They basically told their algorithm what they wanted it to find, and it found it. They told it to take a picture of a black hole, and it constructed a black hole out of random data. I think it's important to note that whenever you're using a neural net machine learning algorithm, you should know that this form of analysis should be used to explore a parameter space in search of a new hypothesis, but not to confirm a hypothesis. When you take all of this together, you start to see a community that maybe has individuals who are perfectly sane, but as a group, their behavior it's insane. The diagnostic criteria for schizophrenia is when you start to see patterns in noise. This experiment is equivalent to saying, look at my picture of a cat. You don't see a cat. You just need to apply the right cat-shaped filters. So from what I can tell, they convinced themselves that they could use measurements that had 100% uncertainty because the uncorrelated errors would cancel out, and they called this procedure closure of systematic gain error. And I wondered, once you give your solution a cool name, the problem is solved, right? They suggested that because this procedure was used in crystallography experiments, then they could use it. But I don't know if they thought about it on a fundamental basis. From what I could tell, this procedure was nothing more than multiplying together the amplitudes and adding the phase errors together. And what I know about basic data analysis tells me you can only add together correlated errors that you want to remove from your data. You can't do this with uncorrelated errors, yet this appears to be exactly what they did. So, what do I mean by correlated errors? I mean things like the sun, something that is very close by and not 26,000 light years away like the black hole that they wanted to measure. So if you recall, they're using telescopes all over one half of the Earth's face to measure something that is 26,000 light years away. They focus their microscope into the blackness of space, and they tell themselves that the light that is leaking around the edges of the Earth doesn't matter. It would be funny if it weren't so true, it's just sad, really. So millimeter wavelengths are strongly absorbed by the atmosphere, but how can we be sure that the measurement wasn't of sunlight leaking around the Earth? There's also a concern about 1.3 millimeter emission of carbon monoxide, and I'm sure that someone from their collaboration wrote a paper about how these two errors could be ruled out based on some analytic approximation or numerical simulation. But all they would have had to do to definitively rule this error out is to compare the measurements they took from the early morning and the late evening. Yet they didn't do this. Their data taking was spread out over 16-hour shifts, and they just mixed it all together. So, based on this, what they did is they took a very good measure, or a blurry measurement of the corona of the sun. But what was reported in the news media was that a PhD student has taken a picture of the first ever black hole. Technology is progressing, front page news. Aren't we great? And the funny thing is that The reaction to this involved men's rights activists loudly complaining about a young woman getting credit for coordinating work done by a team of men. And in The Atlantic, one of my favorite publications, they had a lead story in their science section on smart woman attacked by sexist brutes. I mean, it was just absurd that this managed to get reported in this way, so uncritically. You'd think that the scientific community would have had a more skeptical response, since that's their job. They're supposed to be skeptical, right? So, but instead, what they basically said, nicely done, and returned to their favorite obsessions. People in the scientific community generally do not think that analyzing results outside of their narrow specialty are in their purview. That's politically unwise. These researchers tend to prefer to trust the academic institutions that are responsible for reviewing the work. Instead of getting skeptical, critical analysis, we get publishing via TED Talks and movies that convince young people that black holes exist because they're really cool to think about, even though if you actually understand something about relativity, you know that they are absolutely absurd concepts on so many levels. So, I guess before I move on, I should say that even if they did not make a mistake, even if they did not mistake correlated errors, as in the light leaking around the Earth, for what they wanted to measure, they made a basic mistake in their effort to construct an algorithm that is not biased by the user. They even constructed two different algorithms that were systematically biased by the user, and decided that because they both predicted the same result, they couldn't be biased. Logic! So, where did all of this black hole mania really get started? It turns out that the movie Interstellar was created with help from a Nobel Prize-winning physicist named Kip Thorne, who has been a big proponent of black hole research from both the Event Horizon Telescope and from LIGO, the Gravitational Wave Observatory, which I've written about extensively, but I won't talk about here. Kip Thorne, I think he's in on the joke because he named his black hole in the movie Interstellar Gargantua. It's sort of a nod to this inside joke about big science, government-funded research. And truth be told, whenever I think of the concept of a black hole, I think of a sort of intellectual energy sink that eats the light within the souls of young people who want to understand the world. I think that it's a very cruel thing to do to a child, to encourage them to study these nonsensical objects, because the person who is popularizing them knows that they don't exist and that they are a result of mistaking the map for the territory and for mistaking mathematical approximations for reality. This man knows that black holes are invalid extrapolations from general relativity. He wrote about that back in 1963. But by 1993, he wrote a pop science book explaining how general relativity, it's just one way to describe things. And he even explicitly says that the ability to speak in multiple opaque languages carries power. And if you read between the lines, you understand that this power enables you to bedazzle students and lead them into intellectual black holes, like the Event Horizon Telescope collaboration, or like the project for which he won a Nobel Prize, the LIGO, the Gravitational Wave Observatory, which cost $2 billion to build over the course of decades, and which earned him millions in prize money. So, well, I guess I could say a little bit about LIGO before I stop. But basically, what's amazing in physics is that they're making the same mistakes over and over again. Back in the 1960s, the physics community started trying to measure gravitational waves using magnetometers until they got enough measurements that they all realized that they were deluding themselves. But by the early 1990s, the physics community had forgotten about this magnetometer debacle, and they had decided to build a gravitational wave that was so big and expensive to replicate that it would be impossible for its results to be disputed. And this, what's really funny is if you look into the details, this Nobel Prize-winning device can only be validated through magnetometer measurements. It's the number of mistakes in this particular experiment is equal to the number of the number of errors in the Event Horizon Telescope collaboration measurements. So there are two communities here that commit logic errors at every single level of the project. It's like they're a sink for a certain type of physics student who maybe is capable of doing things but not understanding them. What shocks me about this is that if this is happening in physics, you can be darn sure that this is happening elsewhere, in companies all over the place, that you have sort of this institutional knowledge that makes no sense, but yet people continue to contribute to it. So general relativity is a theory that if you really understand it, you'll know that it's flawed. It's not the law of the land. It's an approximation. It predicts measurable bending of starlight. It predicts the precession of Mercury. But it also predicts these unmeasurable things like black holes, neutron stars, and singularities. What you might not know is that it fails to predict galaxy shape, the redshift of starlight, the flyby anomaly, or anything quantum mechanical. And if you ask yourself why the physics community believes in the predictions of a theory that fails in so many ways, you start to understand the way that physicists think. They're kind of myopic. And when they sort of burn out of the physics community, they are often embraced by the data science community, where they are trained to apply Bayesian statistics. And they might not notice that error propagation on a Bayesian network can produce false confidence and automated delusion. In this form of statistical analysis, you can end up with researchers who do not do enough exploration of prior beliefs by trying wide-ranging priors. They might not put enough thought or funding or time into thinking about confounding factors. They might not do enough exploration of subpopulation and noise composition in a larger population. They might not do enough compensation for non-random sampling, probably due to funding or time limitations. And they might not do enough, try hard enough to come up with simple explanations of experimental biases and issues, which are often relegated to tiny print and lost when media writers play a game of telephone with the original results. Then there's the issue of jargon. The jargon the physicists use is different from subspecialty to subspecialty. The language the Bayesians speak is different from the language the neural net people speaks, which is different from the language that the machine learning people speak. They might tell you any tunable unsupervised machine learning solver uses transfer learning to some extent, sometimes implicity in the form of hyperparameters or pre-processing of inputs. This is relatively similar to what I just described in the previous slide, in the language of Bayesianism. But what they might be forgetting is that complexity is a form of laziness, and it often hides errors, as does specialized subdiscipline syntax. So, when we use these data science techniques to construct an image of a person, how well do these images match with how the person views herself and how others view her? If we do not acknowledge our blind spots, will the picture appear arbitrary, cartoonish, and without nuance? When we peer deep into the void, might we accidentally construct an image of ourselves? As in the case of the Event Horizon telescope, peering into the darkness of space and capturing an image of the Earth, surrounded by the solar halo, corona. Physicists fooling themselves with a complicated machine is a central theme in 2 novels I've written. And I think that novels should be a part of a scientist's training because they teach students how to distinguish between literal and figurative concepts. If you believe that general relativity provides a literal depiction of nature rather than a figurative approximation, you will tend to believe in black holes. And I think this is important to know because science should produce progress, but when it swirls around in eddies of self-citation, you end up with black holes in a figurative, not literal sense. With that, I would like to thank you for your time and ask you to think for a moment about how many weary nights went into the creation of that image of a black hole. I mean, those are people who spent their time doing this. They could have been out living their lives instead.